be privy to all this information as well. So just to be clear, I did update the calendar. I didn't update the other, like the calendar yet, but I will. But just to make sure that you know kind of where we're at. So that says bowling ball. It meant to say bowling ball, and it really should say basketball. So just ball lab would be fine. So today we're going to finish this up, and we're actually going to start some of the displacement velocity conversation. So we're kind of doing both of these. I would like you to do this set of homework, the chapter 2, questions 1, 2, 5, and 6 for homework this weekend. Okay. So if you have not yet done that, that would be great for you to work on this weekend, and we can talk about it on Tuesday. We will not quiz on Tuesday because I feel like we're not quite there yet, but I'm going to plan to have a short quiz, just like a 3-question or something like that quiz at the beginning of class on Wednesday of this coming week. Does that make sense? So if you have questions as that's going, let me know, and then we'll have more homework on Tuesday, but we'll keep that where that is. Sound okay? Awesome. Okay. We are going to jump in where we ended yesterday. And yesterday, I believe that you ended by making a graph. Would you pull that graph out and then maybe also pull out some notes so that we can make some observations? I'm trying to remember exactly where we ended. We ended by writing down some observations. Does that sound right? Oh, yeah, there you go. There's some observations written down there. We doing okay? I know. I'm trying to figure out what I want you to make up for that. I don't want to have you do it all in color because it's going to take too long. But if you want to just kind of sketch, you don't have to write down the numbers, but just kind of sketch what you see there so that we can write some things on it. Is that something? Cool. Okay. Everybody else was serious today? Yes? I'm trying to remember. My memory is failing me. Okay. All right. So taking a look at this graph that we made yesterday, it's so nice and pretty. Your lines are very linear. Your data is very linear, I should say. What were some of the things that you wrote down, some of the observations that you made about this graph? It's so much more fun if you respond. Anything? Yes.
As time goes on, the dots get farther apart.
Okay. As time goes on, the dots get farther apart. What do you mean by that?
So I'm more of like, so if you go, I'm not explaining.
Just give it a shot.
So from blue to green, like if you look at all of the blue, red, and green dots, the space between all of them increases as time goes on.
Okay, that's cool. I like that. That's a good observation. So like looking at the distance between these guys here versus the distance between these guys here, is that what you mean?
Yeah.
Yeah. Do you guys agree with that observation? Absolutely. Yeah. Cool. Thanks. What else? Yeah.
You said the slower the ball travels, the bigger your slope becomes.
The slower the ball travels.
Well, not slower, but like your angle of the line.
Okay. What'd you say? Angle of the line?
I said slope.
Do you like, which one do you want me to write?
Slope.
The slower the ball travels, tell me to write down again. I'm sorry. I just want to get it right.
The bigger your slope becomes.
The bigger. You said bigger. I'm trying to put words in your mouth. Sorry. Bigger the slope becomes. Okay, so let's figure out what that means. So given the data that we wrote down, the experience that we had together, so just to kind of get this in your head, because Patience is like, I wasn't even here for this. Let's talk about what we did. Can somebody explain to Patience what we did? Like in 30 seconds, help her live what we experienced yesterday? We did an experiment.
With Ben as the roller.
Ben was the roller. What was he rolling?
The basketball.
A basketball. So Ben had a basketball. Okay, we're putting it together.
6 groups.
6 groups.
2 on each team.
2 on each team. No, you're getting all the details.
Separate sides.
Okay, we're out in the hall.
Stopwatch.
Everybody was a meter apart. They had stopwatches. Then what did you do once everybody was set up?
I rolled the ball at different speeds.
Okay, so we did it like 8 times or something. So he was doing like the granny bowling. You know what I'm talking about, like this. Yeah, it was really, really fun. Okay, and he'd roll the ball. And then what would you guys do after he rolled the ball? He said go, and what did you do?
Start the timer.
They started their timer. So everybody started at the same time. And then the ball rolled. When the ball crossed your line, what did you do? Stop the stopwatch. Does this sound like it's kind of making sense? Cool. And so then we came together. We decided not to do all the trials because that would have been ridiculous. So we just picked 3 of them. So we did 3, 5, and 7. And so the people at the 1 meter mark put times down. People at the 3 or the 2, 3, 4, 5 for 3 different trials. And then that's what we graphed. Does that kind of help? Okay. So now that we're all on the same page, I want to come back here. So looking at this, even though Patience wasn't there, she can kind of get a sense of maybe what was happening. Thinking back to our experience and looking at the graph, I want all of you to think this through because I'm going to ask somebody. In which of these cases, blue, red, or green, or here, let me number them so that my friends, I always have to keep that in my head here. So this was trial 3. This was that was trial 3. This was trial 5. This was trial 7. In which of those cases did the ball go the fastest? Talk at your tables. See if you can remember because, you maybe remember, maybe you don't, I don't know. In which of those cases did it go the fastest? So how would you guys say? Which one did it go fastest?
5.
Trial 5. So maybe you remember that from your experience. Maybe you don't remember that from your experience. If you were just looking at the graph, like say, I don't know, on a quiz, and you were asked in which case did the ball go the fastest, how would you know that it was 5? Yeah.
Because the label on the bottom is time and then it's like that one's good.
Yeah. So it took only, just a little bit over a second for that ball to go 6 meters. Whereas it took in 7, it took, 4 and 5 seconds, a little more than 5 seconds for it to go 6 meters? It took a whole lot longer for it to go 6 meters in this one than it did in 5. And 3's in the middle, so it's never going to be the fastest, right? Yeah. So if we were going to label these, and all the stuff that I'm writing down here, you are welcome to write down on your paper as well, or on your notes. I'm not going to say you must write this down. Like in my freshman or my 9th grade class, we have note sheets, right? Where you have to write down this thing in this spot. I don't do that for you guys, just letting you know that, okay? This is your chance to figure out how you're going to take notes. So you figure that out for yourself, but if you want help, let me know. So which one we said that 5 is the fastest? And which one is the slowest? 7. Because it took the longest to get to 6 meters? Okay. The slower the ball travels, the bigger the slope becomes. So we need to talk about slope, yeah?
Yes.
You guys have learned about slope in math class? I feel like when I teach this to physicists, some people are like, I love slope. Some of you are like, I hate slope, and I just had to get through that test in Algebra 1. Okay? I don't know where you guys are at. I don't know if you love slope or hate it, but I just want to remind you of what slope is. What is slope? So y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Yeah, does that sound familiar-ish? Sometimes they call it, do they tell you this, rise over run? For some reason, when I was in high school, I really had a hard time understanding what rise and run were. The thing that really made sense to me was the subtraction, or that delta y over delta x. Have you seen that before? Delta up here, right? Boom, there it is. Means change in. So going up a lot over a little bit of space. Yeah. Which one of those graphs has the highest slope? Highest rise over the same run? Which one is the steepest? Higher slope equals steepest, right? Does that make sense? Yeah? Okay. Low slope, less steep. You can also remember that if you're talking about, your slopes, right? I don't know. Again, I don't know exactly what your math experience was, but I can tell you about mine. All right, so this is super steep. I guess like this for you. What slope is this?
That's, zero.
Zero slope, right?
And-
Zero means that there is no rise over a whole lot of run. Zero slope. Bigger, oops, I have to do it the way that you see it, not the way that I need to see it. I'll do it this way because we can do it together. Steeper, 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 higher slope, higher slope, higher slope, higher slope, really, really high. What's this? Undefined, because that means that you've got a whole lot of rise over no run. Can you divide by zero? No, the calculators explode, right? It's bad. Don't do it, right? So yeah, just kind of getting that back in our heads because we're gonna talk about slope today. So I wanna make sure it really makes sense. Okay. So do we still agree with the statement? What's that?
Is that wrong?
That's what I'm asking.
I think it is.
The slower the travels, the
The faster the ball travels,
Yeah.
the bigger the slope.
okay. So we can fix it one of two ways, right? We just don't want to fix both things because otherwise we'd be wrong again backwards. So which way do you want to change it? The faster the ball travels. Okay, so we're going to change this. The faster the ball travels, the bigger the slope becomes. Cool. Yay. We were going to do this anyway, so it's perfect. I love it. All right. Other observations. I'm going to come back to this one in a minute, but other observations that you wrote down? I've got one from that. Let's see. Dots get farther apart. That was Ben. That was from here. So Malik, what did you write down? What's another observation?
I don't think so. But trial one's the fastest because it's the steepest, and southern's the slowest because it's steep.
Okay, so I'm just going to kind of expand on what you said there. So 5 is the steepest and the fastest. 7 was the least steep and the slowest. Awesome. Thank you, Malik. I'll say, did you guys have anything else written down? Any other observations? That kind of, yeah. Emma, what about you guys? Did you have anything else written down, or were those kind of the big things? Okay, cool. All right. Awesome. Well, let's just go with it then. We're going to go with this slope thing. Now, I don't know if you remember yesterday, I was apologizing to you, perhaps even profusely, about the fact that we put the time on the x-axis and the distance on the y-axis, even though I told you before that we never do that, right? Like, we're doing something wrong. There's a reason that we're doing this thing wrong, though, and that was because that slope really matters and because we want to be able to see it. What is the slope of this line? We kind of have said it here. The steeper the line, the faster, the less steep, the slower. What do you think that slope might represent from a physics perspective?
Is it meters per second?
It totally is. It totally is. Meters per second measures what? The speed or the velocity. Absolutely. So really, literally, what we were graphing here was the speed or the velocity. So we're going to write this down. This is a big deal. So right here, we're defining 3 things real quick. We're going to define distance. We're going to define time. That one kind of goes without saying. We've kind of done those already. And then we're also going to define speed or velocity. So you might want to just throw this in your in your notes, but you can put it again wherever you think you'll find it that makes the most sense. We've kind of defined distance already. Distance is from one point to another, from a beginning point to an end point. So how far an object travels. Okay. From beginning to end. Okay. That's how many steps it takes. There's another word that we're going to throw in there as well. Also starts with a D, and it's the word displacement. Displacement is the big physics word. This is the one that you're going to see and use a lot. often the distance and the displacement are the same thing. When we were rolling that basketball, the distance and displacement are the same. Displacement really, literally means the initial position subtracted from the final position. Okay? Usually we write it as X. X is just a position on, like if you think about it like on a number line. Okay? So where did you start? Where did you end? Subtract those two. You guys remember learning number lines back in the day? Okay? The game is, and we'll practice with this a lot in a little while, all we care about are the beginning and ending spots. Okay? So the displacement for our ball in this story was 6 meters, right? It traveled a distance of 6 meters. Okay? You could think about, if you go on a road trip and you drive from here to the Quad Cities, okay, Davenport, Bettendorf, etc. You drive to the Quad Cities, your displacement and your distance would be about the same, and it would be something on the order of like 60 miles or something like that, right? But if you talk about your trip, if you go on just for a day and then you come home, you start, or you think about a day of school. Where do you wake up in the morning? At your house, in your bed, right? You go do a bunch of things. You go to school, you go to work, you go to practice, you we can draw a picture. Where do you end up at night? In your bed. Have you traveled any distance during that day? For sure you have. But what is your displacement from the beginning of the day to the end of the day?
You're home to home.
0. Home to home. Yeah. So distance and displacement are sometimes the same. It depends on when you call your final and end, or final and initial, right? Yeah. This one is the one that we usually use. Both of them are measured in what units? Kilometers or meters, yeah. I'm generally going to use meters. Sometimes we'll use kilometers, though. Yeah. Time is pretty straightforward. Time is measured in what units? Generally seconds, but it doesn't have to be. Right? We can adjust as we need to. Speed or velocity. You guys have probably played with speed and velocity before. But I want to look at it from a literal perspective. Excuse me. On this graph. I'm gonna no, we'll just write on top of it here. We're gonna take some data. I'm gonna do one with you, and then I'll let you do another one. I'm gonna find the speed of the green one, the slow line. Okay. Somebody said meters per second. Meters is the distance. It's the change in y. Are you with me there? Seconds is the change in x. So if I do a change in y divided by a change in x, what am I actually just finding? The slope. Okay? The velocity, I'm going to throw that in there first. Sorry, I keep kind of jumping around trying to decide what I want to write here. The speed or velocity is really just the slope of a displacement versus time graph. That's exciting. It's measured in meters per second. So we're just taking two units that we know and putting them together. It's measured in meters per second. Okay? And it's basically, as I'm guessing, what do you think speed is or velocity is? Like physically, what is it? What did you say?
How fast?
Yeah. That's exactly right. How fast something goes. How much distance something travels in a given amount of time, right? Does it travel a lot of distance distance? That's what we're asking. That's what we're asking. Okay, I'm excited about this. On your graph, let's take a look at that number. No, I lied. I'm going to do number trial 3 with you, and then I'm going to have you try the other 2. That's what I'm going to do. All right. When you're finding the slope of a line, how do you find the slope of a line? What do you need to do? Rise over run, right? So you need to find 2 points on your line, okay? This is an important rule for science, okay? This is different than in math, I think. I don't know how your math teachers teach you, but this is an important thing for me. You may not use your data points to find your slope. Not allowed. Not allowed. The reason for it is that your data points might be really close to your line, but your line is an average of all of that stuff. So we're going to find 2 places where our line crosses or gets really close to crossing something that we can figure out. So I'm going to use these 2 spots right here. So I'm going to put X's on my graph at places that I can kind of find points. So take a look at your graph. Take a look at your red graph, the trial 3. Okay. And see if you can find 2 spots where your line either crosses those, grid lines, or is like right in the middle. Like I like this one because it's right in the middle, so I'll be able to figure out what that is. Okay. And then I'm going to take that information, I'm going to write it up here if I can find a spot. I feel like I'm kind of crowded out here. I'm going to find that data. So I'm going to go ahead and write those pieces down. You can write yours down. So I'm going to say my first point is at, so that's going to be a time of 0.5 seconds and a distance of 2 meters. Okay, that's this point here. Is that making sense? My other point is right here. So that's at 1.75, just because it's right here. It's kind of in between those 2. And it's at a distance, seconds. It's at a distance of 5.5 meters. So go ahead and see if you can find a couple of points that you can find on your graph to determine those points, and then we can look for, then you can calculate the slope. I'm just going to come out and make sure you found the points first. Yep. Awesome. Yep. So I was just thinking of using the red one first. Yeah, how's it going? Did you find some points? Yeah.
Yeah, I told you I was going to find some here. So, what did you do? How is this
You mean like the 0.05 or the?
Those are the dating ones.
Yeah.
Where did you get your data?
So the data for the graph, the track report, came from everybody kind of collected it together. So I can give you that part too if you want. Yeah. So we collected data as a group, and so they kind of wrote it up there, which is why it's all different.
So for the first year, so why do you have so many dots?
So the red dots are these ones. Does that make sense? Are those ones? The blue ones are these ones here, and then the green are those. Does that help a little bit? Okay. Yeah, so you want to try and find places where your line actually crosses. So what I don't want you to do is to use data. So like This spot right here would be really good. Does that make sense? Yeah, and then like this one's really cool. Yeah, right, this one.
Oh, no.
And say, how are you?
It is.
Oh, okay. Kind of fast. Okay.
My dad just likes to watch it.
You totally can. You're not gonna have to turn this. And if you would like to redo it, just to kind of get practice, absolutely. If you want to take a picture of the data, and then you could even like, it's up to you how much you want to accept. If you want to start on the back, you totally can. That's totally fine. And then if you have questions, do let me know. Okay. Yeah. But is the concept kind of making sense? Okay. Cool. How are we doing everything else? I'm playing with the red one.
I see here.
Yes, so like this, you said the line across. Oh, okay, I use like that. And then maybe 80%. I don't know, clear it across the line.
It's a heartbeat.
Yeah. So you want things that aren't actually that.
Tree outside.
Yeah, and then exactly.
I see your yes,
On the left side.
you don't want to
Correct. I want places on the line yes, I would totally do that. Okay, perfect. And then maybe
yeah.
and I usually I like to put X's there so that I don't get confused and think that's data because I know that that's just like a point where I'm looking. So once you have calculated your slope, or once you found your data, then get a calculator out and literally calculate that slope. Find out the speed. I've got calculators over there. I'm missing 2 of them. I don't know if anybody grabbed them yesterday. But anyway, grab a calculator and don't take it with you. At the end of the day, because, it makes me sad. How are you guys doing? Is this making sense? Yeah. Did you get it done? Cool. Do your numbers match? Like, do your speeds match? Yeah? Whoa!
That's what I'm saying.
Like, does your red speed match your red speed? Because they should be about the same check. So I'm going to do change in y, so 5.5 meters minus 2 meters. So if you weren't sure how to calculate the slope, you can follow along with me now. Okay? So I'm doing change in y over change in x. So that's going to be 1.75 seconds minus 0.5 seconds. Okay? A lot of your math teachers say that we just like to leave things in fractional form, probably, because math people like fractions, science people don't. Give me a decimal. Give me a decimal. Just tell me what it is. Yeah. That's another one of those things where we kind of fight in a nice, kind way, where we like each other, but we like to fight too. Probably I'm like the only one that likes to pick fights, so I don't know. Did you guys get something about 2.8? Or did you get something totally different?
I got 3.18.
3.18? Sort of not totally different, right? They're kind of, yeah.
So I got 3. How much of a difference?
So that's kind of, I'm going to ask this to everybody. Is that okay? So Malik just asked a really great question. So let me answer that real quick so that everybody hears. So he said, I got 3. You got 2.8. What are you going to count wrong? Here's the answer. I'm going to look for your work. I'm going to look for what you did. Okay? If I gave you a question on a test and gave you some data, asked you to graph it, and asked you to tell me the speed, that's a lot of stuff, right? So probably if I had a question like that, I would be looking for, did you graph things accurately? Like if you screwed up on the graph, then your slope's going to be different, right? And that's okay. But if you got the graph right, then, maybe these just, you pick different points or you drew your line a little differently. That's okay. As long as I can see where your points are. Oh, these are the points he used instead of the ones that I used. Oh, I can see that you did your subtraction. The answer is really like, whatever. It's the process that I care about. Does that make sense? It's all about the process in physics. It's all about the process. The actual result, very little of my effort is put there. If you got that or got something close to that, I'd like you to also just real quick calculate the speed for, we'll do trial 7 also. So go ahead and see if you can find the speed for trial 7 as well. Pay attention to those units. Again, we're looking for places on this line where the line crosses something interesting, something that you can find, but not one of the data points. So look carefully at your graph. See if you can find a place where the graph crosses something interesting, or a place where you can find the coordinates. If you get stuck, please talk to each other. That's totally fine. Have a conversation. Figure it out. Is that what you got? Hey, that's exciting.
Is the zero necessary?
What's that?
Is the zero necessary?
Not really. I mean, I wouldn't care. I mean, like, I probably wouldn't count them all.
Okay.
Yeah. I kind of like it since it kind of adds clarity, but. Okay. Did you get one also? Hey. Ben, how are we doing?
I had a point. Yeah, I did.
The process.
Yeah, probably.
That is actually after you okay. Go on to the possible one bigger. How are we doing here? Doing okay? Still, yeah. Yep. Yeah. Awesome. All right. Are we feeling good about this? Yeah? Yeah, we love velocity? Awesome.
It's fun.
I love velocity. It's great. All right. Let's see. We're going to do one velocity problem real quick. We're going to start. Today's our very first day of learning problem solving process. Are you ready? So here we go. We're going to do my super simple velocity problems. We'll save my harder velocity problems for another day because I'm going to introduce something else too today. So Malik asked about like how close do they have to be, and that goes not only for calculating a slope of a line, but it also goes for all of the problem solving that we're going to do. Welcome to physics. It's a lot about problem solving. It's a lot of like getting our heads into understanding how things are related and then putting them together, okay? So let me tell you about problem solving. Now, these problems are pretty straightforward because we're starting with the simple stuff. I'm not going to throw you into the like, you know, crocodile pond right away. That would be cruel. I'm going to teach you how to get through it. So we're going to start with some pretty easy stuff. I just want to remind you or tell you the way to solve a problem. The way to solve a problem in physics, the appropriate approach is, and you might just want to write this down in your notes. The appropriate way to solve a problem is to guess. You don't want to guess? You want to know the answer?
Oh, I like want to know what to do. It's just.
I know, I'm going to tell you what to do. I'm going to tell you to guess.
Yeah.
7! That's probably the right answer to some question I'll ask you this year. Yeah. So, you know, just if you write it down for every question, then eventually you'll be right. No, it's probably an acronym. Darn it. It's probably an acronym. Here it comes. G stands for givens. The very first thing on every problem that you're going to do is that I want you to write out your givens, and we'll talk about what that means in just a second, right? U is going to stand for your unknown. Okay. E is going to stand for equation. Okay. S is going to stand for, I don't remember what that S stands for. I don't know, doing some work or something? Some work? There's got to be something better than that, isn't it? I know that the last S is solution. What does that other S stand for? Something like show your work, probably, right? Solve! That's a good one. I like solve better. Must be the beginning of the year because I can't remember any of these silly things, right? Givens, unknown, equation, solve, and solution. Okay? Solution, friendly reminder with units. Okay? So let's give it a shot. Pretty straightforward, pretty easy. Let's make sure we can do it. I'm a big fan of the Muppets. I see it as my role in life to make sure that that cultural icon does not go unknown to the young people of America. And the only way I know how to do that is to teach physics with Muppets. So you're welcome. Yeah.
What are Muppets?
Oh, don't do that. No, I know. Do you not know? Because I
No,
can.
I know.
Okay. I mean, I'm not going to judge you, and I'm not going to change your grade because of it. I just want to make sure. Like Jim Henson is one of my heroes. He did amazing work with amazing puppets, and so I really, really want to make sure people know. So Kermit, we'll have pictures later, but I didn't pull one out today. Kermit is a frog. For those of you that don't know, hi ho, I'm Kermit the Frog. Right? Like that's the guy. He's going to be in some of our problems today. So here we go. We're going to start with some givens. What does that mean? Well, let's find out what that means. Okay, let's write down some givens. So the givens are basically, what do you know? Right? In this question, how far does Kermit walk if he maintains a speed of 1.5 meters per second for 2 minutes? We know the speed. Yes. Now, you know what? I didn't actually write down the equation, did I? On that other page. Sorry about that. It just kind of happened. Let me go back. I was getting so excited. We did it without even thinking about it. But really, what did we do here? We were finding velocity or speed. We'll talk about the difference between them another day, not right now. But I'm going to usually mark it as velocity. V for velocity. It's a little v, not a big V. Big V is for volume. Little v for velocity is equal to, really, what are we finding here? We're finding the difference in position. What is the difference in position?
Displacement.
The displacement. Yeah, the displacement, which we can mark as delta x. Okay, sometimes I'll write that as d, though, because I get lazy. So delta x or d. Keep me honest. Delta x, the change in position, divided by, what's a cool name?
Delta.
Like someone was
That's such a
Delta.
cool name. I love that.
Like a futurist
Delta.
sci-fi.
Like, you know the airline, the Delta?
Oh, I totally know the airline. Yeah.
It's just
Okay.
it'd be a great name.
Let me know when you end up having it. Not anytime soon. Many years from now, when you have a child, send me the little announcement. It's Delta. Like it is kind of cute. All right. And what's going down here? What's seconds A measure of
Time.
time. Boom. All right. So velocity or speed, well, again, we'll talk about the difference later, not today. Velocity is distance over time. Boom. Sound okay? Displacement over time. So now we can use that. Hey, that's good. All right. I'm just going to write that down so I don't forget. Velocity is delta x over t. Okay. How far does Kermit walk if he maintains a speed of 1.5 meters per second? The whole reason I did that was to say that I'm going to write my velocity. So I'm going to write givens here. And literally I write out givens so that I don't forget that that's my givens list. I'm going to write out a list of givens. First one is going to be the speed or velocity. I'm going to write it as V. If you really want to write it as S, by all means, go for it. Knock yourself out. 1.5 meters per second. Always, 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 I am going to, excuse me, include units. Always, always including units. Okay? What else do I know? The time. For sure. I know that the time is 2 minutes. Question. Oh, yeah.
We know that there are 60 seconds in 1 minute.
We also know that there are 60 seconds in a minute. Why do I care?
Because we can convert to minutes.
Right, so that's kind of like a scanning thing. I didn't put this here. The word guess could really probably be expanded to some like 20-letter like acronym of that it wouldn't actually be a word. But yes, we have to look at our units here. We've got meters per second and we've got minutes. That's icky. Let's convert that minutes into seconds, shall we? We did that. We did that earlier this week, didn't we? We got this. There's a reason that we went through it before. Let's do it now. 2 minutes. I want to convert it to seconds. What am I going to put on the top? Seconds. And I'm going to put what on the bottom? Minutes. We're going to play this game. Which one's bigger, a minute or a second? A minute. How many seconds are in a minute? 60. Get how this works? We multiply that in our head or on a calculator if we are not feeling confident. And we go boom. Sound good? All right, givens. Done. Unknown. What's our unknown in this case? The distance or the displacement or the whatever you want to call it. Yes. So we're going to say delta x equals question mark. I would strongly encourage you every time you're making that givens list at the bottom of it, go ahead and put your unknown right there. For this problem, it's going to be pretty easy because we only have one equation to know what we're trying to do, right? But sometimes it gets a little harder. All right. Here we go, team. Time for the equation. V is equal to delta x over t. Now, you can do this one of two ways. You can either plug in numbers first and then solve it, or you can just do the algebra. Okay? A lot of times when I first am introducing this to my physics people, they're like, I gotta plug in numbers. They say, you're wasting graphite. It takes more time, it takes more energy to write all of that out because you've got to write 1.5 meters per second instead of just writing V. You've got to write out 120 seconds instead of writing T. You with me there? Does that make sense? So it can turn really, really ugly really, really fast. That said, a lot of my physics students also like that security blanket of having numbers because numbers make them feel happy. So if that makes you happy, as long as you do it right, I don't care. I'm not going to like force you. I'm not going to like sit there and slap your hand if you did it the other way. Okay? I wouldn't do that. But I'm just going to tell you that I'm not going to do it that way because I like to write this and I want you to kind of start thinking that way because things get more complicated. And by January, if you're still plugging numbers in, you're going to be sad because you're going to have to, like, it's going to be ugly instead of a little bit prettier. Does that make sense? So just kind of fair warning, kind of tiptoe into it if you need to. What are we trying to solve for? We're trying to solve for delta x. It's our first algebra together, you guys. This is like a big deal. This is the first time we've done algebra as a class. I'm so excited. Delta x, we have to get it all by itself.
Do you want to take a picture?
No, I don't. I'm just going to remember the moment. Delta x has to get all by itself. What's happening to delta x right now? What's happening to it? It's being divided by t. You see that? Yeah. How do we undo dividing by t? Multiply by t. So let's do that. I'm actually not going to put this little arrow. I'm just going to do it. Multiply by t. If I do it on one side, what do I have to do on the other side? multiply by t. Yay for algebra together. It's like we should have some songs or something. Yay. All right. And so now I know exactly that delta x is going to be equal to t times v. And now I'm going to plug stuff in. Okay? Now I'm going to plug my numbers in. So I'm going to plug in my 120 and I'm going to plug in my 1.5. Oops, come on, little thing. Why are you being so goofy? I think it's adorable that you wanted me to take a picture, or you wanted to know if I wanted to take a picture. And what do we get? I don't know. Did you plug it in? 180? That makes sense.